James Webb Space Telescope is identifying objects in the dark ages that by best measurements we have are large fully developed galaxies. So who ordered that NASA's $10 billion James Webb Space Telescope has now been in space for little more than 2 years, but the stunning results it's already returned are proving it's worth every penny. Historically, our grandest views of deep space came from Hubble, but as of July 2022, James Webb takes us beyond what anything else has seen, from the faintest galaxies to the richest clusters to mostly empty cosmic voids to the deepest depths of far-off space, and much, much more. The superior telescope has revealed details we've never seen before beyond all expectations. When James Webb focused on large regions of space that appeared blank to Hubble's eyes, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did the stars go? How did they utterly disappear without a trace? Join us as we dig deeper into the shocking discovery made by James Webb and how the disappearance of that many stars might affect our planet and our very future. First of all, you have to know that James Webb outperformed Hubble by more than we expected. When you look at the capabilities of James Webb and Hubble side by side, you would expect that our newest space telescope could do much more in less time, whereas Hubble has a primary mirror that's 24 m across. Webb's segmented mirror spans 65 m. This leads to a resolution that's 270% as sharp for the same wavelength light, and light gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages James Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see in the comparison of its composite image of galaxy cluster smack at 723 with that of Hubble, is doing even better than that. Hubble time is divided up into orbits, as from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 96 hours or 576 minutes of Hubble time, but there's only a total of 4 hours or 203 minutes of Hubble data that's gone into these images, despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 125 hours and got 125 hours worth of data. What's the difference? Location. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere in the way of its desired target, and can only acquire useful data when its target is in full unobstructed view of the telescope. Meanwhile, James Webb is some 15 million kilometers away at the L2 Lagrange point. It always faces away from the Sun, away from the Earth, and away from the Moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency extends to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find the objects that appeared blank to Hubble's eyes, in many cases it can resolve them and examine their properties, whereas Hubble could not even see them at all. This helps us achieve one of James Webb's main science goals: to teach us in the greatest details possible how the universe around us grew up and came to be the way it is today. For instance, nearby Jupiter appears as never before. Its bands, rings, auroras, and moons appear alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging. Spectroscopically, transits detect absorbed light and transmitted light, revealing molecular presences, star-forming nebula display unprecedented details from new young blue stars to gaseous features. James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly. Now a 140-plus megapixel view, it expansively reveals far-flung galaxies. Just 1% of this view contains 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Iral, but arguably its greatest images are of individual galaxies. Webb's views reveal gas dust stars and more central black hole containing core shine in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either they're still erupting their way through their death throes with less luminosity and perhaps obscured by dust, or they just up and collapsed into a black hole without going through a supernova stage. But in the worst-case scenario, the universe is just disappearing and we're powerless to stop it. It's been nearly a century since scientists first theorized that the universe is expanding and that the farther away a galaxy is from us, the faster it appears to recede. This isn't because galaxies are physically moving away from us, but rather because the universe is full of gravitationally bound objects and the fabric of space that those objects reside in is expanding. But this picture, which held sway from the 1920s onward, has been recently revised. It's been only 20 years since we first realized that this expansion was speeding up, and that as time goes on, individual galaxies will appear to recede away from us faster and faster. In time, they'll become unreachable even if we journey toward them at the speed of light. When you look out at a star whose light arrives after traveling toward you for 100 years, you're seeing a star that's 100 light years away due to the fact that the speed of light is finite. But when you look out at a galaxy whose light arrives after traveling toward you for a journey of 100 million years, you're not looking at a galaxy that's 100 million light years distant. Rather, you're seeing a galaxy that's significantly farther away than that. The reason for this is that, on the largest scales, objects that aren't gravitationally bound together into galaxies, groups, or clusters are affected by the expanding universe. The longer it takes a photon to travel from a distant galaxy to your eyes, the greater the role of the universe's expansion, implying that the most distant galaxies are even farther away than the amount of time the light from them has been traveling. This shows up as a cosmic red shift, since light is emitted with a particular energy and hence a particular wavelength. We fully expect that it will arrive at its destination with a particular wavelength as well. If the fabric of the universe were neither expanding nor contracting, but rather were constant, that wavelength would be the same. But if the universe is expanding, the fabric of that space is stretching, as shown in the video above, and hence the wavelength of that light becomes longer. The great red shifts we've observed for the most distant galaxies have absolutely verified this picture. But we can do much more than determine that the universe has expanded and continues to expand. We can use all the information we gather to conclude how the universe has expanded over its history, which in turn tells us what the universe is composed of. Once the light leaves a distant cosmic source, the expanding universe stretches the wavelength of that light. This leads to a red shift, where the more distant objects will have their light red shifted for longer amounts of time, when different components of the universe were more important, by measuring sources at a whole slew of distances, discovering their red shift, and then either measuring their intrinsic versus apparent size or their intrinsic versus apparent brightness, we can reconstruct the entire expansion history of the universe. In addition, since the way the universe expands is determined by the various types of matter and energy present within it, we can learn what our universe is made out of. 68% dark energy, equivalent to a cosmological constant 27% dark matter. 49% normal protons, neutrons, and electrons matter, the 1% neutrinos and antineutrinos, about 0.8% photons, and absolutely nothing else, including no curvature, no cos-MC strings, no domain walls, no cosmic textures, etc. Once we know the components of the universe to this degree of precision, we can simply apply this to the laws of gravity given by Einstein's general relativity and determine the future fate of our universe. What we discovered when we first applied this to the discovery of a dark energy dominated universe was shocking. First off, it meant that all the galaxies that weren't already gravitationally bound to us would eventually disappear from view. They would speed away from us at an ever-increasing rate as the universe continued to expand and expand and expand, unchecked by gravitation or any other force. As time went on, the space between gravitationally bound objects would increase faster and faster, making galaxies disappear from view as they crossed a key distance, the distance where a photon emitted or reflected by an object would never reach us, even if that photon were moving toward us at the speed of light. Today, that distance is about 18 billion light-years away, considering that the observable eye is some 46 billion light-years in radius. This means that only about 6% of the galaxies that are presently in our observable universe are reachable from the Milky Way. The remaining 94% are already unreachable owing to dark energy's accelerated expansion. The future will see these galaxies becoming increasingly distant, and eventually, as they speed away faster than the speed of light can compensate, becoming unreachable and invisible owing to the expansion of the universe. From our perspective, our own local group, which consists of Andromeda, the Milky Way, and about 60 small satellite galaxies, will eventually be all that's accessible to us. As distant galaxies become unreachable, the universe will appear increasingly empty, although we can see tens of thousands of galaxies in a single field of view through James Webb. Today, the only way to reveal that cosmic web will be to look at today's universe and detect those galaxies before they disappear. The accelerated expansion is relentless and gravity isn't strong enough to overcome it. The universe is disappearing, and there's nothing we can do. It's the natural result of a universe with dark energy. The universe is expanding, and we've been able to discover this. The universe's expansion is accelerating, and we've observe this too. As we continue to observe the universe, we'll continue to see this effect, and more objects will become unreachable from the perspective of Earth and the Milky Way. This all might lead you to an inescapable question: if we're all bound for a cold, dead, empty universe powered by dark energy, why is the Big Rip a possibility? Most of us tend to assume that dark energy is simply a cosmological constant, a form of energy inherent to space itself, where the more space we create, the more dark energy appears within that space. If that's the case, distant galaxies will eventually disappear and our local group will eventually merge together. Dark energy would cause the universe to keep expanding forever, but the other bound structures will remain intact. If dark energy strengthens over time, however, it could lead to the Big Rip. The most recent estimates of the Big Rip would mean that if dark energy strengthened, then it would start ripping apart the universe at a certain stage. The original model suggested 22 billion years from now, but recent estimates say 6,080 billion years from now. When it starts, it will rip apart galaxy clusters, and as it continues, it will eventually destroy individual galaxies, the solar system, and eventually individual atoms and even subatomic particles. The Big Rip is a possibility if dark energy strengthens, causing the universe to tear itself apart. If dark energy remains a cosmological constant, the universe will continue expanding with bound structures remaining intact. However, if dark energy evolves and strengthens over time, it could lead to scenarios like the Big Crunch or the Big Rip. The nature of dark energy is still under investigation, but if it strengthens, it will inevitably lead to the universe tearing itself apart. The only question is when, and current estimates push the first step of the Big Rip to 60-80 billion years from now. The accelerated expansion of the universe is relentless, and if dark energy strengthens, it will tear apart galaxies, solar systems, atoms, and subatomic particles, ending with the fabric of space and time itself being torn apart. In conclusion, the universe's expansion driven by dark energy is relentless and unstoppable. Observations show that dark energy's nature and the universe's fate are still uncertain. If dark energy strengthens, the Big Rip will tear apart the universe. However, if it remains constant, the universe will continue to expand with bound structures remaining intact. Observing and understanding the universe today helps us predict its future, but the possibility of a Big Rip remains, reminding us of the preciousness of every moment and the importance of exploring the universe while we can. The discovery of the universe is accelerating. Expansion driven by dark energy has profound implications for the future of the cosmos. As we continue to observe the universe with instruments like the James Webb Space Telescope, we may gain further insights into the nature of dark energy and the ultimate fate of the universe. The James Webb Space Telescope is identifying objects from the dark ages that, by our best measurements, are large, fully developed galaxies, which is unexpected. NASA's $10 billion telescope has been in space for a little over 2 years, and the stunning results it has already returned prove its worth. Historically, the grandest views of deep space came from the Hubble Space Telescope, but since July 2022, James Webb has taken us beyond what anything else is seen from the faintest galaxies to the richest clusters to mostly empty cosmic voids and the deepest depths of far-off space. The superior telescope has revealed details we've never seen before, exceeding all expectations. When James Webb focused on large regions of space that appeared blank to Hubble, it detected something mind-boggling. 100 trillion stars have mysteriously vanished into the void of space, raising questions about what happened, where the stars went, and how they utterly disappeared without a trace. Join us as we dig deeper into the shocking discovery made by James Webb and how the disappearance of so many stars might affect our planet and our future. First, you have to know that James Webb outperformed Hubble by more than we expected. When you compare the capabilities of James Webb and Hubble side by side, you'd expect the newest space telescope to do much more in less time. Hubble's primary mirror is 24 m across, while Webb's segmented mirror spans 65 m, leading to a resolution 270% sharper for the same wavelength of light and a light-gathering power 730% greater than Hubble's. This improvement is due to the physics of optics alone and doesn't include Webb's advantages in cooling, wavelength coverage, and instrumentation. For the same observing time, you'd expect Webb to collect 730% as much light as Hubble, but James Webb has done even better. Hubble's time is divided into orbits. From its low Earth orbit, it completes a revolution around our planet every 96 minutes. 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. Based on simple math, 6 orbits multiplied by 96 minutes per orbit would equal 96 hours or 576 minutes of Hubble time. However, only 4 hours or 203 minutes of Hubble data went into these images, despite nearly 3 times as much time being devoted to this target. For now, we can only marvel at the discoveries being made and ponder the vast, mysterious future that lies ahead. If you enjoyed this content, please subscribe and hit the bell for notifications of future episodes. Your support motivates us to continue delivering quality content. Thanks for watching, and we'll see you next time.